Super, thanks, Neil. So today we have José Piquer. José Piquer is graduated as a geologist from the University of Chile in 2004. During the next 7 years after graduation, he worked as an exploration geologist for Codelco, Chile, the world's largest copper producer. There he was involved in both greenfields and brownfield projects, exploring for porphyry-style and IOCG deposits. He recommended the drilling campaign, which led to the discovery of the Cerro Negro ore body in the Rio Blanco Los Bronces district of central Chile. Between 2011 and 2014, he moved to Australia to complete his PhD at CODES at the University of Tasmania. The topic of the PhD project was the structural controls on the placement of porphyry copper moly deposits in central Chile. Since 2015, he has been living in Valdivia in southern Chile and working as a professor at the University Austral de Chile, where he is currently director of its Institute of Earth Sciences. He has conducted applied research about the structural controls on magmatic and hydrothermal activity in the Atacama Desert, the Andes of central and southern Chile, Patagonia, and the Fujian province in China. So welcome, Jose. Thanks for joining us today. And with Jose, we have a panelist today with us, who is Libby Charman, who is a principal geologist, principal global geoscientist at BHP, working for metals exploration. So I also welcome Libby. She's going to be probably asking some amazing questions. And Jose, it's all yours.
Okay, thank you very much. Thank you, Irene, for your introduction, and thank you to all the organizers of All the Bosses Hub for inviting me to give this talk, and also for the wonderful initiative of organizing all these presentations. So yeah, the idea of this presentation is to discuss a bit this concept of fundamental basement faults and the relationship with the emplacement of magmatic hydrothermal systems, and in particular to show some recent studies in different parts of the Chilean Andes which deals with this topic and which illustrate how some of these fault systems can be recognized in the field or from different types of geological and geophysical data. Yeah, so the first thing I want to do here is just to clarify some of the terminology that has been used to refer to this type of faults. So the fundamental basement fault or fundamental basement structure is a concept which has been used mainly by John Hronsky and his collaborators in Australia. But here in the Andean context, this type of structures have like different names. TLFs, or translithospheric faults, is the terminology mostly used by Orlando Rivera and Gonzalo Yáñez, estructuras translithosférica in Spanish. And other groups, mainly those collaborating with the group of José Chembrano, have used the term ATF, like Andean transfer faults, or ALFS for arc-oblique long-lived fault systems. And this is just to clarify that we might find this terminology in papers or in this presentation, and all of them refer to the same type of structures. They refer to these very long-lived faults which are oblique to the present-day continental margin and to the axis of the magmatic arc, and which were there before the initiation of the Andean orogenic cycle. So what is a fundamental basement fault then? It's a long-lived fault system, which, as I said before, in the case of the Andes, is a fault system which was there from before the mid-Jurassic, which is commonly considered the beginning of the Andean orogenic cycle. It has a high dip angle, and the origin is still a matter of debate. Some of them are interpreted as being originated as suture zones between different blocks of continental crust accreted to the margin of Gondwana during the Proterozoic and the Paleozoic. Some of them have been interpreted as also being active as master faults and transfer faults of rift systems, intracontinental rift systems, which were active in this area during the Triassic and early Jurassic. But the clear thing is that they were there before the mid-Jurassic, before the initiation of the Andean cycle. They have a long trace. They can be hundreds of kilometers, but commonly they have quite small displacement at the present-day surface. And this is because what we see on the surface is the product of the reactivation and vertical growth of a pre-existing deeper fault. So in the Andes, commonly the basement rocks, the rocks of the Proterozoic and the Paleozoic, are covered by thousands of meters of volcanic and sedimentary deposits, And then these faults, when they are reactivated, these basement faults have to propagate vertically through this cover. So normally at the present day surface, what we see is a network of small individual faults with an anastomose geometry, which are not the typical continuous and obvious faults that we see in geological maps. Normally, they are not shown in geological maps, for example, from Geological Service. When we have outcrops of basement blocks in places like the Andes, normally they are bounded by these fundamental basement faults. But normally, as I said before, what we have in the surface here in the Andes is these thick sequences of Mesozoic and Cenozoic stratigraphic units. And in that case, it's still possible sometimes to infer the position of these fundamental basement faults, even if they are not shown in geological maps. But it's possible to infer their location because of sudden and violent changes in the stratigraphic phases and thicknesses and the age of the stratigraphic units, which are many times, in many cases, shown in the geological maps. And this happens because, as these are high-angle faults, when we have extension in the continental margin, they tend to be easily reactivated as normal faults, and they accommodate the location and distribution of deposenters where these volcanic and sedimentary deposits accumulate. So that's why these faults commonly bound particular stratigraphic units. They can also be interpreted from the presence of discontinuities or inflections or changes in the kinematics and the deep directions of younger and shallower faults formed during the Andean orogenic cycle. They can also be interpreted from the alignments of volcanic systems and mineral deposits. This has been well recognized from a long time ago by economic geologists, that mineral deposits tend to occur many times in elongated clusters, from which it is possible to interpret a deeper structural control. And in fact, John Hronsky has made this statement that understanding this architecture of fundamental basement faults is the most important generic aspect that we need to understand for conducting predictive mineral exploration for deposits under cover. This is a cartoon also from the paper of McWaig and Hronsky, which shows this concept of the vertical propagation of a fundamental basement fault. So we have the fault here in the basement, then this is covered by volcanic and sedimentary units, and then the fault is reactivated with it can be with any kinematics, depending on the orientation of the principal stresses at any particular point in time. But then when this fault is reactivated, it propagates vertically through the cover. And what we will see finally on the surface will be a network of individual small faults, which look like might look insignificant if we look only at one of these individual faults, but they have a clear preferred orientation. They can be followed for a long distance, and they are reflecting the presence at depth of the fundamental basement fault. Also, if these faults are oriented more or less perpendicular to sigma 1 at a given point in time, they can act as following this fault valve behavior, using the terminology of Richard Simpson, which means that they can connect with overpressured reservoirs at depth, and which then these overpressured fluids and magmas eventually can be released through these misoriented faults, which misoriented faults means that they are more or less perpendicular to sigma 1 and then are difficult to reactivate unless we have high enough fluid pressure. And putting this in the context of the Chilean Andes, here we have a convergence regime now. This is the current situation. We have a convergence regime trending east-northeast. So we can, doing a generalization, we can assume that in most cases, sigma 1 will be more or less parallel to this convergence direction. And then in that case, northwest to north-northwest striking faults, high-angle faults, will be more or less perpendicular to sigma 1, will be misoriented for reactivation, will require these very high fluid pressures for reactivation, and then will be prone to having this fault valve behavior, which is very important for the formation of large mineral deposits. While, for example, northeast striking faults will be more parallel to sigma 1, will be more permeable, will have a more tendency to delay, to have a stronger dilation, and will allow the more efficient circulation of magmas and fluids, but will not favor the storage of large amounts of magmas and hydrothermal fluids. And this is just to show that these faults also can be recognized by its reactivation under the current stress regime. This is the case of the Pichilemu fault. This is a northwest striking fault recognized since long ago here in the basement rocks of the coast of central Chile. These are Paleozoic metamorphic rocks. And this fault is dipping to the southwest. And in 2010, there was a major subduction earthquake here, an 8.8 magnitude earthquake. And 12 days after the subduction earthquake, this crustal fault was activated as a normal fault, according to the focal mechanism solutions, and produced two quite large earthquakes, one 6.9 magnitude, another 7 magnitude. And it is interesting that it was activated as a normal fault, because this fault is striking northwest, it's a high angle fault, it should normally be under compression and maybe active as a reverse fault. But in this moment, it was activated as a normal fault. And this is related with something which have been shown in many cases, that immediately after a major subduction earthquake, the continental margin is relaxed. And there is a sudden extension of the continental margin. And many of these faults, which are normally under compression, reverse their kinematics in this co-seismic and post-seismic period. So during the subduction earthquake and during the next days or weeks or even months, there is a reversal of the kinematics of these faults. So this is also interesting for mineralization, as it has been proposed by some workers that, like Constantino Podosis, that the northwest alignments of hydrothermal breccias that we see in the Miocene to early Pliocene porphyries of central Chile might have formed during these co-seismic periods, when these northwest faults normally under compression are relaxed and then allow for the sudden release of all the hydrothermal fluids and magmas which were stored at depth. So now that was like an introduction, and now I'm going to show some specific cases of studies in different parts of the Chilean Andes, beginning with central Chile. So we are here in the western margin of South America here. The present-day continental margin is trending almost north-south in this area. And this map shows the regional geology of central Chile. This is from the Chilean Geological Survey. So from west to east, we have a coastal cordillera here with Paleozoic and Mesozoic rocks, which was the position of the magmatic arc during the Jurassic to early Cretaceous. Then the magmatic arc began to progressively shift towards the east. So in the late Cretaceous, the magmatic arc was located here, close to the Central Valley, where the city of Santiago is located. After that, the magmatic arc migrated again to the east. And during the Paleogene and Neogene, the magmatic arc was located here in what is called the western main cordillera. And initially, this magmatic arc was under extension with the formation of intra-arc volcanic basins in the Eocene to Oligocene. And then since the Miocene, these volcanic basins were tectonically inverted. So the old normal faults, which were bonding these basins to the east and west, were reactivated as reverse faults. And during the Miocene and early Pliocene, during this compressive deformation, several plutonic complexes were in place in the upper crust, and some of them led finally to the formation of these two giant porphyry cover deposits, Rio Blanco Los Bronces and El Teniente, which are the two largest porphyry cover deposits in the planet. After the formation of the porphyry deposits, the magmatic arc migrated again to the east to its position now here in the eastern main cordillera. Now looking a bit at the structural geology here, the coastal cordillera is characterized by these fault systems oblique to the continental margin, mainly striking northwest, having well studied by the geologists of the Geological Survey, and they have shown that they control the syntectonic emplacement of Jurassic intrusive units. So they were active, controlling the emplacement of intrusions at least since the Jurassic. Now in the main cordillera, there are a couple of north striking faults to the east and west of the main cordillera, which were, as I said before, like the ones interpreted as the basin bounding faults. But internally, within the western main cordillera, there are no major or obvious fault systems. In particular, there are no obvious fault systems near regional scale fault systems near Rio Blanco, Los Bronces, and El Teniente. So that's what was the topic of several studies done first by Codelco, then my PhD, as Irene said in the introduction, was focused on this. And what we did was to complete a detailed structural mapping of all this area between Rio Blanco, Los Bronces, and El Teniente, collecting hundreds of fault plane data and fault plane with the kinematic information, mainly provided by by the geometry of syntectonic hydrothermal minerals. So this was showing us the sense of movement of these faults at the moment of the emplacement of the magmatic hydrothermal systems. These faults also control the emplacement of several syntectonic Miocene intrusions, as shown in these different pictures. And that led to this structural interpretation of the western main cordillera of central Chile. So here I'm showing the main fault systems, the two porphyry copper deposits, and also in pink, this is showing the location and the geometry of the different Miocene to early Pliocene plutonic complexes to illustrate their relationship with this fault architecture. So as you can see, we have these north striking faults here to the east and west of the western main cordillera, but all the internal deformation of the western main cordillera appears to be mostly accommodated by these high angle northwest and northeast striking faults with a structural architecture very similar to what I showed before for the older rocks in the coastal cordillera. This is to show how one of these, a particular example of how one of these faults look like in the field. This is the Saladillo fault system. It's a fault striking northeast and dipping to the northwest. And this fault was active as a normal fault in the Oligocene, and it allowed the formation of this deposenter where about 800 meters of pyroclastic and sedimentary rocks were accumulated during the Oligocene. Then later, this fault was covered in the early Miocene by volcanic deposits of the Farellones formation up here. And later, this same fault system controlled the emplacement of this dike swarm, which is visible here in the picture, and hydrothermal vein system, the Potrero Alto veins, which is a copper silver rich hydrothermal veins. And both the veins and the dikes cut through the Farellones formation rocks, so they are younger than early Miocene. And the syntectonic hydrothermal minerals in the veins systematically show dextral reverse sense of movement for the moment of the emplacement of these veins. So this fault system, which was active as a normal fault during the Oligocene, during the opening of the volcanotectonic basins, and then it was reactivated as a dextral reverse fault during tectonic inversion of these basins in the Miocene. And this is something that we see for many of these arc-oblique fault systems in the western main cordillera. So looking at the stratigraphic correlations, they appear as normal faults with hundreds of kilometers of displacement. But looking at the kinematic indicators in the syntectonic hydrothermal minerals, we can see that they were reactivated as slide slip faults with a reverse component during the Miocene and early Pliocene. The fault we were looking at is the one shown here in this red circle. And this is part of a larger northeast striking fault system, which can be followed all the way to the coastal cordillera here to the west. And this is also the case for some other northwest, in this case, northwest striking fault system, like the ones shown here, in which it's possible to correlate the faults that we were mapping in the western main cordillera with the faults that have been mapped by the Geological Survey here in the coastal cordillera. So this appeared to be quite large fault system crossing all the Chilean continental margin and very good candidates for fundamental basement faults. The rose diagram up there shows the preferred orientations of the fault planes in this area, and they reflect these preferred northwest and northeast trends, similar to what we were looking at before in the geological map. so are remarkable. The north striking faults are remarkably scarce in this part of the Andes. And the northeast striking faults show a predominantly dextral component, while the northwest striking faults show a predominantly sinistral strike slip component of movement. And this is consistent with the paleo-stress calculations, which reflects that most of these faults were reactivated under a transpressive tectonic regime with east-west to east-northeast trending sigma 1, and with sigma 3 trending north-south to north-northwest, and some groups of faults more consistent with a vertical sigma 3. These arc-oblique faults, which we mapped in the western main cordillera, can be inferred to continue towards the eastern main cordillera, and they appear to be controlling the location and also the geometry of the active volcanic systems there. These are the 3 active volcanoes in this area, and to the right I'm showing the distribution of individual volcanic vents and the alignments of individual volcanic vents in these volcanic complexes. And all of them appear to be very consistent with the orientation of some of the arc-oblique faults that we were looking at in the western main cordillera, in which we're controlling the emplacement of Miocene plutons and hydrothermal systems. This structural architecture also appears to have a relationship with the distribution of upper crustal seismicity. So this is showing again the same faults architecture and the distribution of earthquakes with depths of less than 20 kilometers in this part of the Andes. And they have some clear concentration in some specific areas. So there are some concentrations of earthquakes here following the eastern boundary of the western main cordillera. But there are also some clusters of seismic activity within the western main cordillera, some of them even showing clear elongations of these seismic clusters following some of the faults that we have recognized in the field. And also there are evidences of neotectonic activity in some of these structures. This is a northeast striking fault right to the east of Santiago, where it is shown by this work of Lavenue and Chembrano that these northeast striking faults are cutting through quaternary river terraces of the Maipo Valley. So both from the seismic activity and from these neotectonic evidences, we can see that these faults are still being reactivated under the current stress regime. Now, I want to show some studies that we did in a specific fault system here, which is this one, the Puquencillo fault system. This fault was interesting for us because some works done in the 90s by Orlando Rivera and his collaborators proposed that this fault was associated with a major change in the stratigraphy, in the Cenozoic volcanic stratigraphy of these volcanic basins. And then we published this work in 2017, where based on lots of uranium lead ages of the volcanic units, uranium thorium helium ages for their exhumation, and also based on the interpretation of the chemical evolution of igneous rocks, we proposed that the hypothesis of Orlando Rivera was correct, and that the geologic evolution of these volcanic basins and their subsequent tectonic inversion was quite different to the north and south of the Puquencillo fault system. But still there were very few evidences, field evidences of this fault system. So we completed some field work dedicated specifically to see if there were evidences in the field of this northwest striking fault interpreted from the previous works. These are some pictures of different fault planes belonging to this Puquencillo fault system. The picture in the upper left shows one of the most evident expressions of one of the branches of this fault system in the surface. Also, the fault system controls the emplacement of a beautiful set of silver-rich epithermal veins, the San Pedro de Nolasco veins, which were in place in one of the branches of the Puquencillo fault systems. They are syntectonic veins. They were in place during a sinistral strike slip movement of the Puquencillo fault. These are the preferred orientations of the fault planes along this area, and they show a clear west-northwest preferred orientation parallel to the interpreted orientation of the Puquencillo fault system at the larger scale. And these are the paleo-stress calculations from the fault plane data at the Puquencillo fault system, and it shows that it was reactivated during the Miocene, during the emplacement of magmatic hydrothermal systems under this strike-slip regime with more or less east-west trending sigma 1 and north-south to north-northwest trending sigma 3. Now, the Puquencillo fault system is located here in the western main cordillera, and it can be correlated directly with the Valparaíso fault system, which is have been mapped here in the coastal cordillera by the Geological Survey. And several interesting things happens along this deformation zone. So from east to west, we have the Maipo volcano here, the Escalones prospect, which is a skarn prospect here in the eastern main cordillera. Then we have the San Pedro de Nolasco veins, the Carlota intrusive complex, which is a Miocene intrusive complex, late Miocene. Then we have here the Loaguirre stratabound deposits of early Cretaceous age in the coastal cordillera, and more to the west, we have here the Antenna district, which is a district of gold veins of Jurassic age, all of them occurring along this deformation zone. And also there is a second parallel structure a little bit more to the south, passing through the El Teniente porphyry copper deposits. And it's possible that maybe these two fault systems are the surface expressions of maybe one single continental scale discontinuity present below the Andes in this area. There is a recent work published this year by Argentinian geologists where they propose that the existence of this lineament, what they call the El Sosneado Melipilla lineament. Melipilla is this city located here. And they propose that, so this lineament correlates very well with the Valparaíso fault system and the Puquencillo fault system, with some differences in its strike, but in general, they correlate very well. And what they say is that this structure, its continuation into Argentina to the southeast, is associated with a major regional scale change in the Triassic to early Jurassic seam rift stratigraphy of the deposits in Argentina. So it's very likely that this structure continues another several hundreds of kilometers to the southeast into Argentina. This is also an interesting study published last year by Rebecca Pierce and collaborators. This is about 100 kilometers to the south of El Teniente. And they showed this very clear alignment of seismic events here in the with a west-northwest trend shown in the figure to the left. And then they also provided this magnetotelluric data, which shows that there are some areas of low resistivity here around this west-northwest striking fault. So their interpretation is that these low resistivity zones are large hydrothermal fluid reservoirs at depth, and that this west-northwest striking fault, this ATF, as they call them, the Andean transverse faults, is normally sealed and allows for the concentration of these hydrothermal fluids at depth until the fluid overpressure causes fault reactivation, and then fluids can escape through the fault, and this produces these seismic swarms with these west-northwest alignments. So following a fault valve behavior in the terminology of Richard Simpson. Now I want to show some examples from southern Chile. This is an area where we don't have porphyry deposits. There are beautiful volcanoes and lakes, but no porphyries. But there are lots of very interesting studies here about the relationships between tectonism and volcanism. In this area, we have a major arc parallel strike slip fault, the Ligeniowski fault system. And there are several arc oblique faults, both northwest and northeast striking. And the largest volcanic complexes are located at the intersections between the arc parallel Ligeniowski fault and these arc oblique fault systems. So there are very beautiful examples of that. This is the Kayaki volcano with a very clear structural control provided by a northeast striking fault, which is reflected in the geometry of the volcanic complex, the orientation of the feeder dikes, the orientation of the individual volcanic vents, the alignments of the volcanic vents. And this is the interpretation from Sealfield and collaborators about how is the fault system controlling the volcanism in this complex. They interpret this that is controlled by this northeast striking fault, almost parallel to the orientation of sigma 1. And then this fault has a dextral strike slip component and a strong dilational component, which allows for the very efficient ascent of magmas through the crust. So the volcanic products that we see here are basaltic andesites with little differentiation, little crustal contamination. They ascend very quickly through the continental crust and produce very quiet, like effusive volcanism. The same happens here in this example to the left. These are the Osorno and Puntiagudo volcanoes, also controlled by a very evident northeast striking fault system. And again, these are very primitive magmas, basaltic andesite, quiet volcanic events. While the situation is totally different here in this example to the right. This is the Puyehue-Cordón-Caulle volcanic complex, and this is controlled by a northwest striking fault. And the volcanic products here are mainly rhyolites, highly differentiated, and the volcanic events are very explosive with the release of very large amounts of volatiles. And in fact, another interesting thing here is that the two last eruptions of this complex in 1960 and 2011 were right after major subduction earthquakes. So this is again consistent with the idea that after a large subduction earthquake, the continental margin is extended, and these faults, these northwest striking faults, which are normally under compression and allowing the accumulation of magmas and fluids at depth, these faults are relaxed during and after this major subduction earthquake, and then they allow the escape of all these differentiated magmas and volatiles, in this case, up to the surface. The same has been interpreted for geothermal systems also in southern Chile. So this figure shows in the upper part, in the upper panels, they show faults more or less parallel to sigma 1, which allow for the more constant flux of hydrothermal fluids or geothermal fluids, while in the lower panel, they show an ATF, an Andean transfer fault, a basement fault striking northwest, which is then normally under compression, is normally acting as a reverse fault with a sinistral component. So it's normally impermeable and is allowing for the accumulation of overpressure fluids at depth. And then when we have a subduction earthquake, this is relaxed, the fault is reactivated as a normal fault, and it allows the escape, the violent escape of these fluids which were accumulating at depth. And even this leads to the formation of hydrothermal breccias, of northwest trending hydrothermal breccias in these faults, which make a very interesting analogy with the northwest trend of hydrothermal breccias that we see in the porphyry deposits of central Chile, of the Miocene to early Pliocene belt. This is another beautiful northwest alignment of volcanoes here, the Villarrica, Quetruvian, Lanín. And we had a student here working a short time ago trying to look for evidences of a fault system with disorientation in the basement of these volcanoes. So this there are some outcrops here between the volcanoes of Cretaceous and Miocene plutons. And she was able to find some beautiful evidences of northwest striking faults in these plutons, which control the emplacement of dikes and hydrothermal veins, syntectonic hydrothermal veins, with different kinematics since the Cretaceous. So clearly this was a long-lived fault system which was present there long before these volcanoes were formed. Now to have a quick look at northern Chile. So there we have, similar to what we see in southern Chile, in the Eocene to early Oligocene, there was a major arc parallel strike slip fault here, the Domeyko fault system. And the large porphyry deposits of the Eocene to early Oligocene belt of northern Chile have long been noted to have been emplaced at the intersections of this arc parallel fault system with some northwest trending lineaments. But very few studies have been done to try to look at for the evidences of these lineaments in the field. Probably the one which have the most studies about that is the Calama o Lacapato del Toro lineament here, which passes through the Chuquicamata district and also passes through the Lascar volcano, which is the most active volcano in all of northern Chile. This fault system has been recognized in the field. These are some works done by the geologists from Codelco. geological maps in the Chuquicamata district. So in the map here in the upper left, Chuquicamata is a little bit to the north, and this shows the Toki cluster of porphyry deposits. And there is clearly visible this northwest striking fault system, several northwest striking faults, some of them putting in contact Paleozoic rocks with late Cretaceous volcanic sequences, so with large displacements. And the map to the right shows a more detailed view of the porphyry, of the Toki porphyry cluster. And it shows again very clearly this northwest striking fault system. But interestingly here, the emplacement of the porphyritic intrusions related to the mineralization is not provided, is not controlled by these northwest striking faults. As you can see from this map, all the porphyries are strongly elongated in a northeast direction. So it's very likely that there was northeast striking faults controlling the emplacement of the porphyries, while the northwest striking fault system in this case has mostly post-mineral movements and control the emplacement of post-mineral dikes, and also controls the geometry of the supergene profile of these porphyry systems. Now, if we look at the continuation of this fault system in Argentina to the southeast, it has also been well recognized in the field. There are this beautiful work from Lanza and collaborators with lots of field data about this fault system, also showing that it's seismically active in Argentina. So now we can talk about a Colama or a Capato del Toro fault system, it's not a lineament, it's not just a lineament anymore. And this is a recent work also published by Gonzalo Yáñez and Orlando Rivera, which is probably the most comprehensive interpretation of fundamental basement faults in central and northern Chile. This was based in both geological data, using all the criteria I mentioned at the beginning of the presentation to try to interpret the position of fundamental basement faults, and also complementing that with geophysical information, regional scale geophysical data. And based on all of that, they proposed this architecture of fundamental basement faults in what they call the translithospheric faults, the TLFs, in central and northern Chile. Of course, this is an interpretation. It can be improved, it can be modified with later works and with more field data, but it's, as I said before, probably the most comprehensive interpretation of this type of faults until now in central and northern Chile. And this is the last thing I want to show. This is a work we published recently, and what we did was to compile all the available information regarding the orientation of the principal stresses and the geometry of the porphyritic intrusions and hydrothermal breccias and fault system and post-mineral dikes and veins in all the main porphyry deposits of central and northern Chile. So all the main porphyry systems of the Eocene to Oligocene belt in northern Chile, and all the main porphyry systems of the Miocene to early Pliocene belt of central Chile, which are the largest porphyry belts in the planet. And what can be seen from this is that in northern Chile, in the Eocene to Oligocene belt, and we also have a Paleocene example here, Spence, the structural controls for the emplacement of felsic porphyries associated with mineralization was provided in almost all of these cases by northeast striking faults, which, when they have been recognized in the field, it has been seen that they were active as reverse faults with sometimes a sinistral component, and they were almost perpendicular to the predominant orientation of sigma 1 here, which was trending northwest in the Eocene to Oligocene. And the northwest striking faults, like what we saw before for the Toki cluster, the northwest trending faults commonly controls the emplacement of late hydrothermal veins, high sulfidation veins, post-mineral dikes, but they are not providing the structural controls for the emplacement of the porphyries related to mineralization. And something similar happens in central Chile. So here we have a predominant orientation of sigma 1 trending east-west to east-northeast, and the structural control for the emplacement of felsic porphyries and large hydrothermal breccia complexes was provided by north-northwest to north-south trending faults, almost perpendicular to sigma 1 again, so misoriented faults. And the favorably oriented faults trending northeast to east-northeast control the post-mineral displacements, post-mineral emplacement of post-mineral dikes, the emplacement of veins in the late stages of the evolution of the system, in many cases beginning with the D veins and E veins, high sulfidation veins, emplaced along these favorably oriented faults, but these misoriented faults providing the deeper structural control for the emplacement of the porphyries and the large hydrothermal breccias. So from that, we proposed this model where we show this a misoriented fault acting mainly as a reverse fault, controlling the emplacement of the felsic porphyries and the breccias, and a more favorably oriented fault system, more parallel to sigma 1, producing this post-mineral displacement and controlling the emplacement of post-mineral dikes and late mineral veins related to sericitic or argillic alteration. And then the question remains open about what can trigger the release of these overpressure fluids and magmas which were stored at depth. So one possibility, as I mentioned before, is the reversal of the stress field and the fault kinematics during post and post-seismic periods. Another possibility is the dilation of these misoriented faults due to movements on a conjugate fault system. And another possibility is just that the fluid overpressure reach a critical magnitude and by itself produce the reactivation of these misoriented faults and allows the escape of the hydrothermal fluids and magmas. So to finish, these fundamental basement faults are long-lived fault systems in the case of the Andes present there before the Andean orogenic cycle. High-angle faults, they play a first-order role in the ascent of magmas and hydrothermal fluids through the crust. They have been reactivated several times with different kinematics depending on the orientation of the principal stresses, and they are associated also with different magmatic hydrothermal products, depending also in different points in time, depending also, as I said before, on the orientation of the principal stresses. Their origin, I mentioned before, that is still a matter of debate, as suture zones between continental blocks, as the master and transfer faults of rift systems. But the clear thing is that they were there before the initiation of the Andean cycle in the mid-Jurassic. They have been obliterated in many cases by Andean faults parallel to the continental margin. They can be covered by younger units. So sometimes it's quite hard to recognize them in the field, but it can be done with detailed geological structural mapping and with this interpretation of different types of geological and geophysical data. It is very relevant to do these efforts for mineral exploration, of course, and it's also important for understanding other things like the structural controls on active volcanism, structural controls on geothermal activity, and also for the seismic hazard associated with this type of arc-oblique faults. And I think that's the last one, yes.
Thank you so much, Jose, for such an amazing talk. I have to say, in the world of ore deposits, we don't have that many work done in such a large scale, and which is fundamental for better exploration and understanding of how these deposits form. But first of all, I want to invite Libby, who is here as our panelist, to see what questions does she have for Jose, so we can start the discussion.
Yeah, thank you, Jose, for a really interesting talk. And I always enjoy these kinds of presentations that deal with a lot of different scales, and the idea that you can apply the same principles to, you know, a country scale as you showed, but also right down to understanding the deposit scale and what's controlling your emplacement of mineralization events. With these translithospheric structures, one of the things I always battle with is how to represent them on a map in terms of width, for instance. So you showed us a bunch of different maps, some of which had these things mapped as quite thin lines, and then you had the large blue zones, and obviously you have the fault splays and everything that's happening at the surface. What's your feelings on what the actual surface extent of these big architectural structures are?
Yeah, so yeah, I think that sometimes they are like simplified and showed as single lines, but a more realistic thing to represent them is to like these blue white zones I shown in some of the interpretations, which might be tens of kilometers wide maybe, And it will depend on how much cover do you have, essentially, because this relates with this thing that I showed in the beginning of the vertical growth of these faults. So if you have the basement exposed at the surface, these faults might be quite narrow. And there are some examples of that in Argentina, for example, where you have exposures of basement rocks. Sometimes these faults are relatively narrow and they're very beautiful, like with ductile deformation and mylonites. And but then when this is covered by thousands of meters of stratigraphic units, then these faults have to propagate through that. And that's the more the faults have to propagate vertically, the more they're going to disperse into several individual faults. So if they have to do that, if they have to propagate through a lot of cover, then they are going to be quite a quite wide zone. And it's going to be more challenging to identify like where precisely is the fundamental basement fault at depth. And that will probably need some help from maybe geophysical data or other types of interpretations. Yeah.
Yeah, and just one more question, if I'm allowed, as the sort of informal panelist. You mentioned cover, and I think that's the other one, especially in Chile. And it was great to see that map come up that does seem to be resolving a little bit of the cover bias on these architectural maps. But you mentioned geophysics. What other ways do you think there might be to better map these features under cover? Especially in things like if they're in gravel terrain, you know, they're coming up through gravel terrains and maybe you're not even seeing a propagated fault structure. What sort of other techniques would you recommend to fill in those cover bias gaps that maybe we have?
Yeah, I think apart from what you might interpret from geophysics, so the key is to get all of the possible data that you can get from the geology around this covered area. So all of these things I mentioned early in the presentation, like trying to, first of all, of course, do detailed structural mapping in the field, because this strong preferred orientation of little faults in some specific areas can mean that there is a larger fault system at depth, which is propagating vertically. So having a lot of structural data, of course, helps a lot. And also interpreting these major changes in the stratigraphy, which sometimes can be extracted from geological maps, like from the geological maps from the Sendageomin, from the Geological Survey. Sometimes you can see that there are some very sharp interruptions on, for example, a Jurassic stratigraphic units, and it's interrupted, and then it's a Cretaceous unit after that, and this contact is not mapped as a fault, but it's like a very straight contact, very violent, which probably it's reflecting the presence of the fault there. And if it's possible to have a look at all the rocks in the coastal cordillera in the basement, also sometimes there these faults are more clearly visible. And also looking at, as I said before, the alignments of intrusive units, the alignments of volcanic centers in the active volcanic arc, and trying to put together all these different types of geological information, and from that try to interpret the trace of these fundamental basement faults and where the traces are in the areas under cover.
Perfect. Well, I'll hand over to Irene and Neil, because it looks like we have a couple of questions coming through in the chat.
Irene, I guess I'll toss in Lyle Harris's question. So Jose, what is the link, if any, between the conjugate faults you describe and structures with the same orientation in the subducting slab?
That's an open question, I think. So there are a couple of interesting things happening regarding the interactions between the subducting slab, things which happen in the subduction channel, and these faults in the upper plate, these translithospheric faults in the continent. There are many signals that there is some sort of interaction between that. In the paper that we published about the Puquencillo fault, we showed that there was a seismic swarm in 2017, and these were earthquakes in the subduction zone, so they were not earthquakes within the crust, but the seismic swarm was clearly located where the Puquencillo fault and this other fault system parallel towards the south are located in the South American plate. So there appears that there is an interaction between the subducting plate and maybe some features in the subducted oceanic crust, like fracture zones or seamounts, ridges, and this kind of features in the subducting plate. What happens in the subduction channel and what we see in the deformation of the continental crust. I think there is some kind of links between them, but we don't understand them really very well until now.
Okay, no, thank you. That was a good answer, but I've been looking at the gravity data, especially the satellite gravity, and it really looks like a lot of the more dominant faults that you're describing just continue for a long way beyond the continental crust. And I was also intrigued to see there's a paper in 2019 by Carrasco et al., and they show the map of the same geometry of structures in the subducting slab, exactly as you were describing, but just from the gravity, and of course you haven't got that fine resolution, it really looked like the same structures were just keeping on going from the subducting plate into the area you were describing. So I don't know if you've looked at the gravity data.
I haven't looked at that gravity data towards the oceanic plate. I have looked at the gravity data in the continent, but I haven't noticed that you can recognize the same pattern in the oceanic plate as you were mentioning. That's very interesting.
Okay, thank you.
Mm-hmm.
Thank you, Jose. I have a question also. So we've been talking mainly today about porphyries, but in your description you said you also have experience exploring for IOCG systems. And I saw that in the Yañez and Rivera paper from 2019, some of the basement faults are actually aligned with some of the biggest IOCG deposits. Have you seen something similar with IOCG deposits during your experience exploring for them?
Yeah, definitely. So some of these, some of the fault systems that are shown by Yañez and Rivera, when I was exploring for IOCG deposits, for example, in the area around Casualidad, that's near Taltal, this area also, there's a major northwest fault system which has been mapped in the area of Taltal. It's called the Taltal fault, and which clearly has a very important role in the structural controls of IOCG deposits in that area. And if you follow that fault system towards the southeast, is the one which passes through El Salvador and it keeps going into Argentina. So there is, of course, a role played by these basement faults in controlling the IOCG deposits. And in particularly for the large IOCG deposits, like the early Cretaceous ones, I haven't looked at that in detail. Probably you have a much better idea about that. But I would expect that also they should be controlled by mostly misoriented faults also, because they are associated with a much larger accumulation of hydrothermal fluids than the smaller IOCG deposits of Jurassic age. And I think that, well, that has also a lot to do with the fact that they were in place during the initiation of the tectonic inversion of the Mesozoic basins and at the beginning of the first pulses of compressive deformation in the latest early Cretaceous. So I would expect that they will be controlled by misoriented faults more or less perpendicular to sigma 1 during these compressive deformation periods of the late early Cretaceous.
Thanks, Jose. Amazing insight on the subject. I think Neil has some questions also.
Hey, Jose. Yeah, from a personal standpoint, that was awesome. Just looking at the different scales of it all, just looking at the big picture. I think for my first question, might be a little basic, but just thinking about specifically El Teniente and Rio Blanco, Los Bronces. El Teniente, as you know, is a large breccia complex compared to a more typical porphyry system such as Los Bronces. And as you showed in one of your slides, there's a significant gap or change from the north and south portion of the block. Do you have any interpretations or opinions on to if those sorts of translithospheric faults, those basement structures, have anything to do with the actual morphology and timing and the style of mineralization in that particular belt?
Well, so if you compare Rio Blanco Los Bronces with El Teniente, I think they are both like related with a very large amount of hydrothermal breccia. So Rio Blanco Los Bronces is also similar.
Okay.
Yeah.
Okay.
Yeah.
Okay.
Yeah. So they are both like porphyry deposits, but dominated by hydrothermal breccia complexes. Both mineralized breccias and also post-mineral breccias like the Braden breccia in El Teniente or the La Copa diapreme in Rio Blanco Los Bronces. So I think the position and orientation of these fundamental basement faults have a lot to do with the geometry and the orientation of these breccia bodies and also felsic porphyry dikes in these two deposits. But I think the fact that they have that very large amount of hydrothermal breccias is more related with other like regional factors, not specifically with the fundamental basement faults. Because, for example, the porphyries in northern Chile, the Eocene to Oligocene belts, that one is more like a classic like porphyry system with very few or small hydrothermal breccias, but mineralization is mainly in different veins, different types of veins. And there are some works proposing that this is related with the depth of emplacement of the systems, and also that it is related with the exhumation rate at the moment of the emplacement of the systems. So I think both of those factors, like the depth of emplacement and the exhumation rates, are more related with like regional scale tectonic events and the rates of compressive deformation and uplift and exhumation, than with the geometry of specific faults.
And I guess RJ has popped a question to the chat, which is kind of along the lines of the next question I was hoping to ask. So I will start with RJ's question, which is, he says, you mentioned that the porphyry mineralization is associated with the northeast structures in the north and the northwest in the south, and suggests that the advanced argillic epithermal systems are later associated with northwest structures at north and northeast in the south. How does this relate to the evolution of the magmatic chamber?
So yeah, the earlier stages of the evolution. So so at an early stage, you have the structural control for the ascent of magmas being provided by these misoriented faults, northeast striking in the north or northwest striking in the central Chile. And this, because they are misoriented, for the magmas it's much harder to ascend through these faults. They tend to be stored at depth, they differentiate, they accumulate large amounts of fluids, and finally they are released and they form the porphyry alignments. Now, in both cases, it seems that in later stages of the evolution of the magmatic chambers, when probably you have most of the magma already crystallized, but still some amount of magmas and fluids left, at these later stages, some favorably oriented faults became available. Maybe they propagated through this area, and they became available for the ascent of these magmas and fluids. And then in both cases, at the late stages of the evolution of the magmatic hydrothermal system, the fluids and the magmas began to ascend through these favorably oriented faults, northwest striking in the north and northeast striking in central Chile. So they come late in the evolution of the magmatic hydrothermal system and of the magma chamber, which is crystallizing at depth. And
just to sort of follow up,
they can still be part of pre-existing faults. Okay. It's only that like hydraulic connectivity, where in the place where this porphyry deposits was being formed, become available in these late stages along these favorably oriented faults. But they can be the result of the propagation of pre-existing faults, like the case of the Calama or La Capato del Toro in Chuquicamata, for example, in the Toki cluster. So probably the the Carama or Lacapato El Toro as a whole existed as a fault system since long ago. It's probably a fundamental basement fault, but it propagated towards the area of where the porphyry deposit was formed in the area of Toki and Chuquicamata only in the late stages of the evolution of the system. It was not available before.
Okay. Mm-hmm. And just to tack on to RJ's, and RJ is a good friend, question. You mentioned that, you know, that I think you were talking about the southern provinces of Chile, specifically in the northwest oriented systems, you had more evolved magmas, and northeast systems that appeared to be more primitive basaltic andesites associated with those sorts of fault systems. So Kocho Podosis said, like, years ago, like he was talking about, you know, when you have in the compression regime, you had the porphyry intrusions being stored at depth, and then when you have that release of an extension, that you could basically intrude the porphyry system. Now, knowing what we know about magma mingling, do you think in these systems, do you think we could, this is sort of the model that we're going to maybe towards, like that we are allowing different intersecting fault systems of structures that allow magma mingling? Or is that just kind of no,
absolutely. Yeah, I think there is a lot of work still to do with this regards. I think the model that we proposed is a generic model has a lot of different specific situations in different individual porphyry systems, and that appears to work quite well with the empirical data that we have from the Andean porphyries. But I think there are lots of processes, like, as you said, related with the magmatic processes, magma mingling, and lots of other things that we still need to understand about what's going on in the magma chamber and how it relates with these fundamental basement faults. So yeah, there is still a lot of work to do, but I think what Kocho Podosis has said about the emplacement in particular of the porphyries in Rio Blanco Los Bronces, the porphyries and the hydrothermal breccias in Rio Blanco Los Bronces, appears to be very consistent with what we see in this case of these volcanic systems of southern Chile, and also, as I showed before, to what we see in general in the porphyry systems of central and northern Chile. But yeah, there is still a lot of work to do in that regard. There are some other interesting work which I didn't show here because of time, but for example, there is a work by Tibaldi studying the magma paths in the altiplano of northern Chile, and it's very interesting because he shows that the magma paths for the volcanic system is controlled almost exclusively by the pre-existing faults, like northwest striking faults and north-south faults. They are not following the ideal orientation, like parallel to sigma 1, which is normally predicted for dikes. Like usually you see a dike and you say, and it was very common to assume that the dike was more or less parallel to sigma 1 and perpendicular to sigma 3, because that's how they are supposed to be in place. But what this work by Tibaldi shows is that magmas are finally going to follow the pre-existing structures, and is easier for a magma to penetrate a pre-existing weakness zone, even if it is misoriented. It's going to be harder for them to ascend through that structure. They're going to take more time, they're going to differentiate, but it will still prefer to ascend through a misoriented fault than to produce a new fracture in homogeneous rocks. It will still require less energy.
Cool. Thank you so much, Jose. And thank you so much for answering so many interesting questions. I think we're on time to finish this presentation. Again, thank you everybody for coming today. Thank you, Jose. Thank you, Libby. Thank you, Neil, also. We will be seeing everyone in a couple of weeks. We have our Kickstarter career path, so everyone is super invited to participate. And that's it, I think. So thanks again, and hope to see you guys in a couple of weeks. Bye-bye.
Thank you.
Ciao, everybody. Take care. Thank you, Jose. Gracias.